So good afternoon, everyone. Welcome to the Netherlands Process Technology Symposium. Normally, it's the NPS is organized every year to bring together the community of Dutch process technologists from both academia and industry in a real-life face-to-face conference. Of course, this year, due to the uncertainties with COVID, it is organized as a series of online webinars. And today is one of such webinars. And today we'll talk about the topic of water. Last week was about circularity, and next week we will talk about health, foods, and pharma. So this webinar is recorded, can be also viewed by you later online. I would like to ask everyone to please mute your microphone and turn off your camera if you are not presenting or speaking. If you have any questions or remarks, please write them in the chat. You see the symbols here on the screen. If you know Teams, of course, you can find it as well on the top of your screen. And if you write your questions and remarks in the chat, then we will address them plenary. And you can also then post those questions to all of the speakers and panelists yourself. So my name is John Harinck. I'm a program manager at the Institute for Sustainable Process Technology. And if we can now go to the program or the next slide, please. Yeah, so exactly, thank you. So today's session, we have a keynote lecture of Professor Kees Buisman, and that will be a keynote lecture about water, all the specific aspects that he will address. And afterwards, we'll have a Q&A, question and answer session, and that will take in total half an hour, the keynote plus the Q&A. And afterwards, we'll start with the panel discussion. And we'll have we have invited 3 extra panelists in addition to Kees. And we will pose a number of propositions to the panelists and also to you at home. And we'll ask everyone to vote. And I'll explain later how that works. So first is the keynote lecture by Kees Buisman. Kees is a full professor at the sub-department of Environmental Technology at Wageningen University in the field of biological reuse and recovery technologies. And his specific interest and focal point is on bioelectrochemistry, if I understood correctly, and novel methods for fermentation and biological induced solid production, both for the recovery of energy, chemicals, and minerals. And in addition to a full professor, Kees is also the executive board member or unexecutive board member of WETSUS, the European Center for Sustainable Water. Your work, and please, the floor is yours.
Well, thank you. Then I'm going to share my presentation. I hope you can see it now.
Yes.
Okay, my name is Kees Buisman. I was already introduced, and I was asked to give an overview of the vision how water technology would evolve in the coming years. And as a matter of fact, we just finished our research plan for the next 10 years. And I thought, since this vision is completely embedded in this, I thought it would be very nice to go through this WETSUS research plan. And then, yes, it works. And we have 4 chapters in this plan. First one is sustainable water. Second one, healthy environment. And the third one, recovered resources. And last one, drought resilience. And I want to go through these 4 chapters with you in this 15 minutes. But before I do that, I want to show you first the vision of WETSUS, that we have defined the water technology as an enabling technology. In the past, in the Netherlands, water technology was not really a science field, and actually it still is not really a science field. It is becoming more and more defined field, and also now it's part of the top sector already for 10 years. So slowly but certainly that water technology is getting its own field in the Netherlands, but it has many disciplines. So we have many universities connected to this field. And but it's also connected to many different industries, and therefore we call it enabling, because for some industries like municipal water, it's the key technology, but many other technologies industries can only exist thanks to the water technology they use. So we want to bring all these water technologies together, so that we, as the Netherlands, can have one of the biggest programs in the world on water technology, because we also have all these industries. And you see many logos of industries that are connected. And we try to bring these industries in by promising that we will work on technology that can deliver them more competitiveness. And now with the Netherlands, we are a mission-oriented research strategy from the government. We have these 4 impact areas that I just mentioned. Of course, we cannot put all the logos in this figure. So if you are interested, that here are all the logos, and you see that we have small companies, large companies, public companies, international companies, and it is very interesting that with the help of universities, many technical small companies can develop new technologies that can be used by the big companies, and the public companies that are there, like the water boards and the drinking water companies, they can guard that the policy of the new technologies that are developed can be applied in the future, so that we are not developing things that we never get permits for. So this is a kind of a model. We are doing that now for 17 years. And in my opinion, it is becoming pretty successful. So let's go to the F. In the first place, the sustainable water. And here we want to develop natural chemical-free treatment technologies for water, for drinking water, for wastewater, for cooling water, for all kinds of water. And what we have seen, of course, in the past in environmental technology is every time you start using chemicals, that in many cases, in the end, you will get new problems. So the Netherlands is world champion in producing chlorine-free drinking water. So I think this fits very well with the Netherlands. And I give you some examples of things that we are working on now and will be working on for the coming years. So for every field, I want to give you a few examples. And in the first place, this is this biological activated filter. And this was developed as a cleaning technology for membrane treatment. And here you see the factory that is built for Shell to produce clean water for their operation in the eastern part of the Netherlands for the enhanced oil recovery. And they developed this activated carbon technology, and they clean them every so many times with pure oxygen. And they are already running for 13 years, and they found out it removes all kinds of medicine rest which are in the sewer water that is treated here. And you see, without adding any chemicals, I consider oxygen as a natural chemical. It is clear it's not absorption by the carbon. It must be that these chemicals are really destroyed by the oxygen and the bacteria. So this is one of these examples, but it's actually a little bit too expensive to use this at all wastewater treatments of the Netherlands. So the research is now on to see how we can optimize this technology so that it becomes more available. Another example is the green polymers. As you maybe have read in the newspapers, that this granulite that has been discharged in the Dutch sand holes leads to very much public uprising, and that is because this granulite has been dewatered by not natural chemicals, and these chemicals, the effect of them is very suspicious, although of course the official government says it's not suspicious. If you look in literature, you can see it is an unwanted chemical in nature. But the dredging companies are doing this everywhere in the Netherlands, where they dredge, they have to dewater, and these chemicals are used and then are released in nature again. So it would be fantastic if you would have bio-based, biodegradable polymers that you dewater it, then you discharge it in these holes, and then the chemicals would slowly but certainly disappear and have no effect at all. So this is what we mean with chemical-free, natural chemical-free approaches. Now, the last one is membranes. So membranes, of course, are in principle chemical-free, but in many cases, many chemicals are used to run these membranes. So wouldn't it be very nice if we would have now my house telephone is ringing. Wouldn't it be nice if we have membranes that we can run chemical free? And here you see the electrodialysis membranes that have been developed thanks to the Blue Energy project we are running. So it's a new approach to the membrane technology. The second topic is healthy environment. And what we mean here is to use all kinds of modern sensors, but also self-learning data programs, artificial intelligence, that we can predict more real time if things are going wrong or not. Just both for things that are happening for our health, like drinking water, but also for discharges, so then it is for protecting the environment. And one example of that is our technology that we use ultrasound waves to predict if pipes are going to break. So when a pipe breaks, everybody knows it, because then you probably have a water fountain. But the trick, of course, is to know when pipes are going to break. So when do you need to replace them? And so normally drinking water companies replaces large sections all at the same time because they don't know. And if you look at if you could predict when you need to replace drinking water pipes, you could save billions in the Netherlands alone on these replacements, because they are very expensive. So we're going to build an artificial intelligence-based platform monitoring the actual status of these pipes and combined to this modern sensors of ultrasound. The second one is working with lights, photonics. And in this case, we bring this light guiding, I call it a glass fiber into the soil, and then we can measure real time the groundwater flow, which is kind of impossible at this moment. And I tell you, with all the pollutions we have in the ground these days, it's very important to know how the groundwater flows, and if you can direct the clean groundwater around the pollution so that you don't have to clean the groundwater. And remember, in the Netherlands, more than 50% of the drinking water is still coming from the ground. So this is very important for drinking water companies. And finally, this is based on the new technology with genomics. It's becoming so cheap now to look at, for instance, bacteria in drinking water, but we can also do this for wastewater. We can combine the data from the genomics with the physical data and chemical data that are easy to measure. And then we can integrate all this data into an integration system with machine learning. And then we hope we can develop this real-time virtual sensors that, for instance, can for drinking water can easily say if it's safe or if it's not safe. And at this moment, in many cases, we only know 2 or 3 days after the drinking water was not safe if there was something wrong with it or not. And that would, of course, be fantastic if we could know that already before we drink it. So this is this is based on all these modern technologies. The next one is more in the field that I'm also working at Wetses, at Wageningen, sorry, this is all Wetses. And as you know, the circular economy, taking the sink of your roof and bring it to the sink recycling, that is easy. But in the water system, all the sink is leaking away. But also all other things like phosphates and nitrogen, everything is leaking away because it's low concentrated, diluted, and to recover that is a little bit more difficult. So that's what we want to focus on. And now we have a whole field of polymer recoveries, and the PHA, of course, is the most well known. This research started in Delft, and at Wetses we have now all the old technologies of Veolia, who is a big water company who stopped with this, and their research manager is also part of Wetses now. And now we can bring all the knowledge we have in Europe, we can bring it together and try to speed up this technology. And it was just announced that the first large pilot plant is going to be built at HVC in the western part of the Netherlands. And then for the first time, we will produce enough material of waste-produced PHA to do all kinds of tests with it. Another one is ammonium recovery. We have, of course, it's very difficult to recover this in an energy positive way. And at Wetses, we have developed a technology that uses electrochemistry. And the hydrogen that is produced in the cathode is fed again back to the anode. And in that way, it is becoming an almost energy neutral system that can be scaled up and recover the ammonium at a very fast rate. And then you get this ammonium, you can get it recovered in ammonium nitrate or ammonium sulfate. And this is a way that we hope that we don't have to destroy the ammonium anymore, like we do with the denitrification and the NMOX processes. But then we can really recover it and save the production of the ammonium at the same time. And this is an electrochemistry development. And another one, but that's a precipitation technology, is that we recover the phosphate that is in wastewater as iron phosphate. And the bacteria produce then, they can convert this iron phosphate into magnetic iron phosphate, which is called vivianite. And with just an industrial magnet, it becomes then very easy to recover this vivianite from the sludges from these wastewater plants. And we have built a pilot plant, and we can show now that more than 90% of the phosphates in wastewater can be recovered in this way, with virtually no real adjustments of the existing wastewater treatment plant. So we believe this could be a very powerful technology to solve the phosphate recovery problem. Just I want to stress that these are just a few examples from our program, because we have more than 50 projects, so that would be a little bit too long. And then finally, it's our new team, that's Drought Resilience. And what you see in the world is that there is about 2 billion hectares of degraded land, where the equilibrium with this water has been broken, and deserts are remaining, but they were not deserts in the past. And to show you how incredibly powerful this can be, I show you this example of the Lus Plateau in China. And the Chinese decided in 1995, this is an area as big as France, so this is a pretty big area. This is the original ground where the whole Chinese culture is coming from. And it has been destroyed by over exploitation, and they started to regreen this, and in incredibly short time, it is completely green again, and you have little streams of water again, and the soil is no longer flushing away. But this is an area where there was enough rain. So if they make plateaus and get the plants growing, the rain could be absorbed by the ground again. And so this is a special case of what you can do in these areas where there is enough rain. But the picture I showed you, where I started with, is the Sinai Desert. And in the Sinai Desert, there is not enough rain. So we need to first try to understand how to get the rain back. And to give you an idea, on the left picture, do we still have time? Yes. And the left picture, you have to realize the wind, which is full with water from the sea, is blowing over these deserts. But the concentration you can achieve at the sea is not enough for condensation. And because the land is so hot and dry that the air increases in temperature, so the condensation point goes further away. And since there is nothing to evaporate water, the concentration of water in the air is also not increasing. Then normally there is a range of mountains around these deserts. Then the heat, the wind with water goes up, and then the temperature goes down, and then you would have the biggest chance of condensation. But that doesn't happen because there is not enough water in the air. So if you would have a forest in these places, then the forest would take care that the amount of moisture in the air is increased. And if then the wind goes up against the mountain, you would get rain. But there is no forest anymore in the Sinai. So could we, with technology, develop a new kind of evaporation system that could create the same amount of moisture as a forest? And then the nature would take care of the condensation. So in fact, you would have a seawater desalination system where you add a little bit of vapor to the air, and then the mountains will take care of the condensation of both what you added and what was already from the sea. And in that case, you would produce massive amounts of water for almost almost like 1 cent per cubic meter. With that water, we would grow a new forest, and when the forest is taking over the task, you can take this grid and put it in the next desert. So that's the fantasy we have about this technology, and the big dredging companies are part of this because they believe that they are the companies that are able to do this kind of technologies. And then the last example is that the other thing you can do is bring more organics into the soil so that the soil becomes more a sponge. And also in the Netherlands, this is becoming important because the moment it is dry, then it becomes drier and drier. So if you would have a lot of water stored in the soil in your organic matter, soil organic matter, then you would have kind of a new evaporation source that could help produce rain again. And well, one of the things that we are doing on for that is that in the Netherlands now we are exporting our manure because there's too much phosphate. And here we have a project, we try to recover the phosphate from the manure and also the nitrogen. And then the manure can stay in the Netherlands, increasing the soil organic matter. And the nutrients that are a problem for the Netherlands can be brought to areas where there are not enough nutrients. So this is the last example I wanted to give. So I hope with this 12 examples and 4 areas to give you a little bit of an idea where we believe that the water technology field will be going to in the next 10 years. So thank you very much for your attention. This was my first presentation ever for a webinar.
I think a very good one. Thank you, Kees. Very interesting presentation. A very good, nice overview also that you gave of all the activities at Wetsus and Wageningen University. If anyone in the audience has any questions, please feel free to ask them. You can add them, write them in the chat, and then we address them plenary. There's already one question or one remark by Arjan van Nieuwenhuizen. Arjan, would you like to elaborate on your, I think it's a suggestion or a remark that you gave?
No, just in addition to Kees Buisman's nice presentation. Thank you very much, Kees. On ammonia recovery, that there are now also some physical-chemical ways of recovering ammonia, which have been proven successfully at Waterfabriek Wilp, for example. Just an example. But thank you very much, Kees.
Yes.
Thank you, Arjan.
But this is also physical chemical, huh? So.
Yeah.
So many different, or not many, at least there are several options and different technologies being developed. I think that's always a wise thing to develop let's say a scale or a range of technologies if the challenges are large. We have another remark or question by Steven Snijders. To your question.
Still a little bit how the technology will work that you will use to evaporate additional water in these deserts. You were referring to some kind of grid, but yeah, can you elaborate on that a little bit?
Yeah, so at this moment, we have started with meteorological studies, because meteorological people are more used to predict the weather, to describe the system, than to actively trying to change it. And with them, we're trying to make a model that where in the deserts this technology would have a success, because if you start evaporating on the wrong place, then it probably makes no sense at all. And so from that knowledge, from that model, we we have not started with it yet. So this is a vision. We will start for developing these grids. And in my fantasy, you would have a grid that can evaporate water. You pump in seawater, and you let the brine go back into the sea. And then, yeah, you have to understand that we already know that these grids have to have a minimum area. So let's say 10 kilometers by 10 kilometers at least. So these are pretty big things. But yeah, but if the effect is what we expect, then the value will be enormous. If you could regreen the Sinai, that the value of that is that is not to catch in an amount.
Okay, thanks.
It's the size of the Netherlands.
Yeah, thank you, Stefan, also for your question, and thanks for Kees for answering it. I think it's time that we can go to the panel discussion, and where we have also opportunity for for everyone in the audience to vote online, and you can do that as shown here in this slide. You can either do it with text or via internet. You go to pollev.com and enter the code given here below. And from then on, you can see the questions and vote for the answers that you think represent your opinion on these propositions as best as possible. Next slide, please. So let me also take the opportunity to introduce the panelists. First is Onno Kramer. Onno is a technologist for the public water cycle organization Waternet in Amsterdam, where he explained to me he's also doing his PhD at TU Delft and affiliated with a number, working together with a number of universities. A very busy man. Thank you for joining, Onno.
You're welcome.
Thank you. So Nora Sutton is associate professor at the Department of Environmental Technology at Wageningen University, and she focuses particularly on understanding the fate and transformation of micropollutants. So, of course, a very important topic as well, and I think we'll also address that in this in one of the propositions. And we also have Kees Wessels, who is a CEO of Cirtec and CTO of Salvation. And he has a broad experience within the world of wastewater and process water technology, and his specific expertise is on the application of dynamic screening of influence and recovery of valuable components from sewage, as well as sewage treatment and management. Thank you, Koos, also for joining. And of course, Kees is also part of the the panel. So very warm welcome. And yeah, I would like to hear your opinion on the next propositions that we're going to show. First proposition, what should be the main priority for water management? Is that water should be used for food production, or water should be used for energy production and storage, for instance, in the case of hydrolysis for hydrogen production? Or should water be used for manufacturing industries, or for drinking water and sanitation, or for harvesting valuable components and elements from wastewater? And of course, if you have any other opinions, what you think is important for water management, then please add them to the chat. I will address them then plenary as well. I see that most of you think or believe that water for drinking water and sanitation is most important, and secondly for food production. Panelists, do you have any? Would you like to share your opinion with us? Perhaps Onno, you work at Waternet.
Yes, thank you. Since I'm a drinking water engineer,
exactly.
I'm really happy with the answer, but
yeah.
I'm a bit stubborn. I think it's a combination of all, because it's not only drinking water, there's more. There's flood protection, we have wastewater treatment, we have the water cycle. So perhaps combination, that's my answer.
Combination. And if you would have to choose, is there any, let's say, if you would have to prioritize because of water stress,
yes.
because of, let's say, low availability of water, there have been 2 years ago, even in the Netherlands, some periods, some summers where there was quite some water stress, some droughts. Yes. What would then, in that case, be your priority?
Public health. So I would choose for drinking water treatment, because we cannot last 1 day without water. But other people will say when we don't have dry feet, but yeah, in a hot summer, that's not a problem, of course. But I would choose for drinking water in this particular case.
Drinking water, okay, okay. Is there anybody else that has a different opinion on that? I see many people choose food production as well as being very important. Koos, what is your opinion on this? Do you have a what is your views on this?
Well, maybe I should say, of course, harvesting valuable components, but I don't know. I think that the priority is first, I would say, drinking water and sanitation, because it's a primary need for all of us. And the other things are consequences for the fact that we use water for drinking water and sanitation. So in that respect, I agree with Onno.
Okay, all right. Nora.
I was at a visit to London, to the water board of London, and they made a calculation how much it would cost if London would not have water for 1 day, or if the sewer would not work for 1 day. And they were so shaken with that, they built a complete spare water factory in the Thames that is for seawater desalination, just for the case that they have too little water.
And their tubes are more than 200 years old. Do you know that? Really?
Yes. But the new sewer, they built a mega sewer all over under London. It's a $1 billion dollars project. It's unbelievable. So you can see what will happen to a city without water. It's within 1 day. It's an unlivable city. It's all the banks close.
Yeah.
Quite some large projects, large measures, capital-intensive measures also taken to mitigate the risks of these very important public risks. I see we have a comment by Peter Dowdy. Peter, would you care to share your thoughts on this?
Well, yes, thanks for this. If you want to prioritize.
Sorry to interrupt. Please also, if you can mention your affiliation.
Okay, yes, I'm Peter Dada, working at the University of the TU Delft and in the PDN course. I think using price as a mechanism to prioritize will solve many problems, because you have water for drinking, you have water for washing, you have water for growing food, and the economy will solve this issue for us. And then if the water becomes expensive, then people are going to make more water, because then you can sell it at a high price. So many problems will be solved by that.
Okay, so you believe in let's say the value of the, let's say, the market, free market, that can solve these kind of issues. And I think that this is one very important point. We'll also address it in one of the next propositions. I do also see that we have somebody that does not agree with this. Stephen, would you care to let us know why you don't agree?
Yeah, well, we know that I think most of the money is within the 10% wealthiest people among Earth, and especially companies like Shell and stuff like that have a lot of money and can, of course, in these dry periods, buy the water simply by spending their money, while the poor people cannot afford the water at that time. And if the price rises, then they will just die or something, or how does this work?
Well, maybe if I can make a comment on that. If we buy water in the Netherlands, then there will be not less water in Africa. So they're not connected, those systems.
No,
True.
So, please go ahead.
No, go ahead.
Oh yeah, I can say something. So personally, I grew up in California, so a place where we have been water scarce for now all of my lifetime. And what you see there is that so individuals saving water because their water prices go up is one part of the story. But in the end, the price that we pay for drinking water is the price is built out of a variety of different components, and only a small portion of that is actually the price to produce the water itself. So the vast majority of that price is related to the piping systems, the infrastructure, having the drinking water treatment plants there. And so what they've seen in California is that changing the price a little bit or even significantly can only affect people's behavior so much, because you have that base price. And what we also see in California is that a lot of the water consumption actually goes for food production. And food production is, of course, really big business. I think something like over 90% of the almonds in the world are produced in California. But those are really water-intensive industries. And so it's the question, you know, where do you draw the line between economic benefit to that state, and where do you say, well, we do have to retain sufficient water for drinking. And one other thing that I really miss on this list is actually the environment. So we require sufficient water to ensure biodiversity in the Netherlands, to prevent seawater intrusion, to retain biodiversity in our freshwater lakes, etc. Yeah, so I don't think price is the complete solution by any means.
Yeah, very good point. Sustainability of not only our, let's say, society, but also the environment. Indeed, very important point. Thanks for that. I think we will continue to the next proposition. And the next proposition is: what could be an important way to reach sustainable water usage in the Netherlands? Is that whoever uses it cleans it? So basically, you have to close the water cycle. Or is it B, increasing the price of drinking water, increase awareness of its value? Or more incentives for agriculture to radically change to crops and animals with lower water demand? Or more incentives for the industry to recycle wastewater in water-intensive processes? Or could it be an important way to convert seawater into potable water? Or do you have any other views or opinions on this? All right. So we do have some agreement or some majority that would say that the most important way to reach sustainable water usage in the Netherlands is to have more incentives for the industry to recycle wastewater in water-intensive processes. And if you remarks or or opinions, please add them write them in the chat, then we can address them here. They're very welcome.
Shall I say something?
Yes, please.
So I think it's very important if you use the water and then discharge it again. In other words, it's still water and goes back into the river, you can use it again. or that you do something with the water that's evaporated, like growing plants. And in the Netherlands, of course, the data centers that evaporate an enormous amount of water, and other industries that use cooling towers. And you would say that the Netherlands, with the River Rhine, would never really become without water. But if you have to choose, then you must make a very big division between the ones that uses water and discharge it again, and the ones that evaporate it. And especially the ones that evaporate it are the ones that are, the more dangerous ones for the total water shortage in the end. I would say that in the world, in the Netherlands, we have a lot of sustainable water because of the Rhine. But in the world, the groundwater reserves that have been built up in millions of years, they are depleted. And that is very unsustainable water. So I would also add to the activities that the Netherlands will not import products produced by unsustainable water anymore, like cotton from India, or all kind of soya from the prairies of the United States.
Yeah, interesting point. So that would require a complete value chain, the water footprint throughout the value chain, and the production also of products being imported. Okay, very interesting, original point. Would anybody like to add to that? Nora, what is your opinion on that?
Well, so what I see here is the division is quite sector based. So industry should reuse their own water, and agriculture should reuse their own water and reduce their own usage. But I think also really important is to consider how can we link these water cycles together. So how can we ensure that wastewater from domestic sources then after that be used in the field runoff can then be used via streams for the industry, and this requires quite a bit of reorganization actually of how our water sectors and our water cycles are currently organized, and requires linking them to each other, both in terms of quantity but also in terms of quality. So making sure that the domestic wastewater effluent that we want to reuse in agriculture is of the right quality. So I think, interlocking or interlinking these different nodes in the water cycle is very important. Okay, so that would be a way of cascading basically water use from high quality to lower quality water, if I understood correctly. Yeah, high quality to low quality, or from one use to the next, depending on where there's supply and where there's demand. I would not say cascading and then disposal. So I would say cascading and then upgrading. Yeah, great, thanks. Who voted F? I'm very curious. There are a number of people, or very few ones, but who thinks or has an idea that is not mentioned here in A into E? If so, please let me know. I'm very curious. Onno, what do you think about, or do you have any strong opinions about this, or what did you choose? What would be the best way to reach sustainable water usage in the Netherlands? Oh no, I believe you're muted. Onno.
Sorry, I didn't see that. So when we're talking about sustainable water, I think about the long-term approach, right? And I give you a silly example. If we have a look at Libya, it's a huge desert. 15 years ago, approximately, there was an organization who built 3-meter pipes, and there was a huge water production, but in 50 years, it's gone, right? The source is completely gone. So that's not sustainable. So that's causing a huge problem. The River Rhine in the Netherlands has a throughput of 2,000 cubic meter per second. So in 1,000 years, I guess still we have a River Rhine. So I think the solution lies in closing the loops. And the previous speaker had a really good point about the way how you buy your products from other countries, which is less sustainable. So closing loops locally, or perhaps a little bit further, it's more complex, but we have eager young minds here on the chat, so we will find solutions. But we have definitely to change the linear economy to a circular economy and reuse all kind of precious minerals from the water, like Kees explained. And yeah, I keep it at that.
Okay, very good, good point. So we have to look at the entire the picture from a holistic approach.
Absolutely.
Not only at the local level, but also at the global level. As also indeed, as you said, also Kees stated. Very good. We have some agreements with in the panelists. I'm also looking for disagreements. Let's say, opinions that are opposite to each other. I think there's a lot of things to be discussed still in the area of water. Are there any more questions in the audience? And if so, please write them in the chat, then we can address them.
I also have one more remark about the price.
Yes.
I think in the Netherlands we pay separately for cleaning the water, for transporting the wastewater, and for the drinking water, including the transport. But the price you pay as an average family is about the same. It's about 125 euros for drinking water, 125 euros for sewer, and 125 euros for the wastewater. But if you all would bring that into the drinking water price, people would be much that saving water could. And in other countries, this is in many cases this is the case. So if you then water your grass with this expensive water, it's a different ballgame. And so I think in the Netherlands we could easily do this. And then the average price of every family stays the same, and only the people that start saving water, they will have a lower price.
Yeah, interesting. And does that work in the? You mentioned some other countries use this pricing system. Do they have good experience with that, or are you aware of?
Yeah, I think so. I always see when I was working at the company park, when we are visiting customers, if there is a payback time of anything that you do, you have much more enthusiasm with everybody. Like look at the solar panels everybody puts on his roof. Everybody calculates the payback time. So you would have then the same for drinking water. And now nobody is calculating anything because it's so little. Yeah. You can never get a payback time.
So cheap, yeah.
For households, that might be doable, but if you go for industries, what you get is basically more concentrated wastewater. So it won't be a solution for industries, these kind of solutions.
No, it's more for people that want to have green grass.
Yeah, great. That interesting point indeed. Any other suggestions or questions or views on this? I think otherwise we can go to the next proposition. All right. Let's go to the next proposition. Yes, thank you. Which states or where do you see the biggest opportunity to reduce micropollutants in water? This is, I think, an interesting topic to many of you. We already mentioned it in the introduction that we would discuss micropollutants. So where do you see the biggest opportunity to reduce these? Is that at the source by regulating and limiting the use of pollutants? Or is that to optimize current water treatment processes by absorption and filtration, etc., or to innovate by developing and using degradable alternatives for these micropollutants that have the same use or application, or by developing new treatment processes such as photocatalysis, or do you have any other ideas, or do you know of any other innovations taking place? So many of you say biggest opportunities at the source to regulate and limit the use of pollutants. No, I think I see that you are burning with to give an answer or to give your opinion on this.
Answer A.
Go ahead.
Answer A would be obvious, but I would definitely choose C. So according to the chemical abstract services, there you have more than 100 and almost 140 million different chemical compounds, right? So it's impossible to remove them with a advanced treatment plant. So yeah, if industry produce biodegradable components, then a huge part of this problem will be solved. So I will choose C.
Okay. Nora, this is very close to your field.
Yeah, so I would definitely agree that C is a really important part of the puzzle. So ensuring that the pesticides we use and the pharmaceuticals we use are as degradable as possible. Nonetheless, we still have a lot of work to do. So I think Kees said something to the extent of we still produce over half of our drinking water from groundwater. And indeed, we do produce a lot of our drinking water from sources that already have these micropollutants. And so that means we will have to also innovate, develop sustainable and economically feasible remove some of these compounds from existing water resources. So I would say a combination of C and D is required. And I would be hesitant to implement B throughout the world, because if we start spending a lot of money on advanced treatments and those innovations, then in a way we also inhibit the innovation required for C. So we say, well, we'll just clean it up instead of also stimulating innovation and developing new and degradable compounds.
But should we not do it both at the same time? Because these innovations, indeed, let's say they can take a long time to develop and then to implement. In the meantime, we're still producing many of these micropollutants, and maybe even in growing numbers. How do we deal with that? The problem we have right now.
Yeah, so we're producing, I don't know how many new chemicals come onto the European market every day, but it's astonishing how many different chemicals are available in our daily lives. And so I would definitely agree that so developing technologies to treat those is an important part of the puzzle, but I would still advocate also developing new sustainable treatment processes based on biology and based on natural processes, and not throwing activated carbon and ozone at the end of every wastewater treatment plant, because then we are creating a lock-in when I think there's a lot more innovation to be done in micropollutant removal technologies.
Got it. So you're advocating for avoiding the problem and not by solving or mitigating the when it has occurred already. So prevention is very important.
Yeah, prevention, and that's for everyone here to think about what chemicals are in their shampoos and their body washes, and what do they use to clean their house, and where's their food coming from. So that's also and not just regulating away all of these chemicals, but thinking about how much of them we consume on a daily basis. Yeah,
that's a good point. A good point. Maybe that's not mentioned here, but that would fall then under other. The public awareness of the micropollutant becoming or being an issue. So if anyone has experience with that, or also would like to add to that, that's also very welcome. Thank you, Nora. I'm very curious, Koos, you also work in wastewater and recovery of valuables, and I'm not sure. What is your opinion on micropollutants? Is that an issue also in your business? And if so, what is your?
Yes, of course. In the basics, I would say that if you have a problem, you should solve it at the source. So the first A would be the primary solution. But if you would ask where is the biggest opportunity, I also think that this will take quite a long time to achieve something. Like with the development of alternatives, it's very important. But I think that the first major step could be made by optimizing current processes, because I don't think that we should wait another 10 or 15 years before really addressing this topic. And I think there's technology available already to make some steps there. So it should be a cascade. First optimize what we have, make some steps, and in the meantime also look for more sustainable alternatives. And try to raise the awareness and solve the problem at the source. So it's not one solution, but I think that the biggest opportunity would be, at least at the shortest term, in optimizing current treatment systems.
Okay, thank you. I'm curious, Onno, what is your opinion on this? Do you have personal experience with this, or in having to choose between some of the options given here? Or
I was already.
I gave you two examples. We talked about shampoos with microbeads. It's really harmful for the environment, right? So there's a solution, and you can replace those microbeads by sustainable products like calcite, for instance. There's this product called Naive, where we use from the water softening process, we use calcite grains to replace microbeads. That's really nice. But let me tell you something else. Is we were talking about advanced technologies, etc. But we have to also, and that's what I'm missing here, invest in the new generation, the students, because they have to in the future, they have to solve our problems, right? So it's also a way that we have to change the curriculum at the universities, right? About making, increasing the awareness of the young students, right?
Mm-hmm. Okay, thanks. That's a very important one. I think that many of the people in the audience would agree with that. I think we have quite a large number of students and PhD students and researchers as well. I see Arjan van Nieuwenhuizen, you would like to add something to this. Please unmute your microphone, and if you're there.
Yes, thank you for the opportunity to reflect a little bit. Nora, I completely agree with you that the first measure should be at the source somewhere. But as water sector, and we are here together in a session about the water sector, we don't have so much influence on that kind of measures. Legislation is not done by us. We can have some lobby there, but that's it. But we can change the water treatment solutions, improve it, make it more sustainable and more effective. So at the end, we should take a responsibility there from our expertise and our investments. Waternet, like Onno, I agree completely how you approach it. As the water sector, we should take our responsibility there, and that's where we can make the changes.
Okay, thanks.
But if you look at the PFAS, which is impossible to remove in a natural way, natural chemical-free way, so you need very aggressive UV radiation or other chemicals to break the PFAS rings. And slowly but certainly, some of these compounds are now illegal, but the whole family of PFAS is still allowed, and new chemicals are coming to the market. It really has no sense for the water sector to start trying to remove them if they are not becoming banned. And the second thing, I just read this paper in the newspaper, the Volkskrant, about pesticides. How many pesticides are in our food, and how many cross toxicity there will be, and how many of these pesticides are never really tested for toxicity. And the majority of the pesticides we get into our body are not from the water sector. Our drinking water is very clean, but the food we eat, it's full with pesticides. So we cannot do anything about it until they are banned. So option A, if we not do something there, that is dweilen met de kraan open, we say in Dutch. So it's we never get it right for the nature. It's impossible.
Yeah, so we need a range of, again, a number of to work on a number of these measures and ways to reduce micropollutants. Okay.
And can I just add one thing? I think for the water sector, so I agree with Arjan. The water technologies is your core business, and that's definitely something you can. That's the effect that you can, your area of effect, so to say. And I think it's very important to always remember that with these micropollutant discussions, public perception is also really important. So we, as the water sector, also have a responsibility that our consumers of water feel safe and are really getting the best drinking water that they can. And so then I can imagine that using technology sometimes to remove or to ensure that your drinking water is of the highest quality is also an important factor.
Perfect. Thanks for this, Nora. I think we're out of time. This was a very interesting proposition, also a very interesting discussion. I would like to thank everyone for attending. Especially, I would like to thank the keynote speaker, Kees Buisman, and also panelists Onno, Nora, and Koos for being with us and sharing your opinions and views on this as experts. Thank you very much. Thanks also to the audience for sharing your opinion and giving feedback and asking questions. And I would like to thank the people from TU Delft and ISPT for organizing this behind the scene. So this session will continue, or this webinar will continue, with a session on for the networking and pitching for PhD students and researchers on the area of water management and water treatment technologies. And everyone is free to stay and attend that meeting, to make the most of this event. Though we cannot organize it face to face this year, this I think is a very nice opportunity to do so. All right, thank you so much. Thank you, everyone.
Thank you.
Thank you.
Okay, welcome everyone to the networking session. We all know it works much better when there is free food and free drinks, but unfortunately that was very difficult to organize. We have a pitch from David. Are you there?
Yes, I'm here.
Hello. So we have a pitch from, I cannot see you.
Yeah, I'm here somewhere.
Yeah, there you go. We have a research pitch from David Fernandez Rivas from the University of Twente. Do you want to share your screen immediately?
Yes, I'll try that. Let's see if it works. Does it work?
Yes, we can see it. He's a group leader, a faculty member in the Faculty of Applied Sciences at the University of Twente, and he's going to tell us about water and bubbles.
Yes, all right. Well, thanks for the introduction. I have a picture of a beer glass in one of my slides, but I think none of us can really enjoy it. So just to tell you a little bit more about what I'm doing. So I'm an associate professor, but I'm also entrepreneur. So I started a company, and I will tell you in 1 or 2 slides during my presentation about what the company is about. And well, why bubbles are important is that what I will share with you in a few minutes is a very fast progression from technology readiness level 0 up to 9. So I don't know how many of you are familiar with ultrasonic bath, ultrasonic technology. I will tell you a little bit more in the following slides. But most people are familiar with a small size applications. But actually, I'm looking into scaling up, well, these ideas into something even bigger than this. So this is an industrial ultrasonic bath. There's a truck here, and there's a technician here. So all that I will tell you, even though started as a micro-reactor technology concept, and now is some sort of mesoscale reactor system, it has the potential to contribute to water remediation. And for that, I'm collaborating with a water utility company in the west of the Netherlands, and KWR, so Water Research Institute, and we're other partners. So as I promised, I have here some beer. I don't know how many micropollutants are there. I drank it in Switzerland a few years ago. But if you have done this experiment, or at least put some carbonated water, you might know that typically you have this sort of bubbles rising up from the bottom, because there's typically a crack at the bottom or some impurity that allows for some gas bubbles to remain there. And well, as the saturated level of the liquid with the given gas, in this case CO2, is quite high, then this bubble can grow, detach, and a new bubble is formed. So if you keep, let's say, doing that for quite a long time, you can have interesting effects, like getting drunk if you drink too much. But what I want to tell you goes more into sonochemistry, and why this is important is because well, for many years, at least 60 years, people have been looking at the effects of ultrasound, principally at the radical formation, because you can break molecules inside the bubble because the pressures and temperatures are very high when you compress the contents of this water, of this bubble. to the point that you can get actually plasma formation and light emission from the bubble. But you also have some interesting phenomena like shock waves, streaming, and jetting, and I will show you a few of these things. But what I decided to focus is on where our bubbles are created, because I thought that if we want to improve the efficiency of these sonochemical reactors, which are notoriously known for very low efficiencies in the order of 10 to the power of -6, so I thought, let's give it a try there. So that's why I always invite people to finish the drink. But why this is really interesting from a chemical or physical point of view is that, well, let's assume you have a piezo material that is oscillating, and you have it, say, in contact with a liquid volume. Then you might have a bubble that can grow and collapse and grow and collapse. And at a given moment, then you have all these conditions required for what I just mentioned: radical formation, sonoluminescence, etc. When you have a proximity of a bubble to a wall, then yeah, the surface is deformed, and then you get a liquid jet. And this is why typically ultrasonic equipment is used for cleaning. So this is an actual video of how a bubble jets towards a surface. So these are very small bubbles in the order of, let's say, 300 micrometers in radius. But why this technology has not really picked up until now, even though it's, let's say, very friendly towards the environment, because only with electricity you can create a lot of radicals. I only illustrate here OH just for simplicity, but you can get a lot of interesting chemistry. But the problem is that to really reach the industrial scales, you need to control many aspects at different scales. And well, this is what I've got busy in the last few years. And I will just give you a little bit of a flavor of how we ended up commercializing a product in less than 4 years. So it all started with a small microreactor. So this is a very small version of the beer glass that I just showed you earlier. So we have a silicon substrate. We perform some artificial modifications, so small cracks at the bottom of this substrate. And then we look from the microscope above what happens when you apply ultrasound there. And then there's a short video here that, so I'll let it run a little bit. So it has some text that explains by itself. So I hope you can all see and read. So the 30 micrometer dimension is indicative, can be a bit larger. Also the frequency can be lower, can be higher. And then we have access to quite fast cameras here in Twente. And so you will see now what happens and why we say that we have tame or control cavitation. So when you reduce the power or the electrical amplitude to the piezo, you can decide whether to have bubbles or not. And if you look with a higher frame rate, so in this case 10 million frames per second, you see that is quite, I'd say, a violent situation there. And well, what follows is a bit more of a physical description. So these bubbles like to talk to each other. So I'll scroll a bit faster. But the interesting thing is that due to this interaction of the bubbles with themselves and any surrounding boundary, you can use them to actually clean objects. And well, just to remind you, there's a millimeter from here to here. And if you put close enough a surface with a contamination, which could be biofilm caused by bacteria, or if you want to clean a membrane, so you can use these bubbles to locally detach any contamination you might have there, like some cake. And then, well, the typical question we get in microfluidics, what happens when you number up? So I can show you what happens with 3. If you ask me what happens with 4, well, it's kind of logical to have a cross. But we kind of skip those steps. So from 3, we went to like 100 and even more. So I'll show you very soon what happens. If you follow Star Wars, I wanted to put Star Wars here, but some of my colleagues were not so tech-oriented, or let's say nerdy. And well, we have a small prank here for those of you who like music. And so we created the acoustic band, the bubble band, but well, it's ultrasound. We don't really know what they are playing. But then moving on to the most serious part is like these bubbles are chemically active. So as I mentioned earlier, they generate radicals. And then when you measure these radicals and you calculate the efficiency of the reaction by multiplying the energy required to break the water molecule into OH and H radicals, and by the production rate and divided by the electrical power, you get a feeling, or actually an obvious message, that when you have 1, 2, or 3 of these modifications, you get a boost in the efficiency. But of course, after a given value, you cannot really extract that much efficiency, because some of that extra energy is not going to create more radicals, but is going to the formation of the bubbles, shockwave, and all the phenomena like jetting that I introduced earlier. To make a long story short, there's a small advertisement. It's less than 1 minute, but this is the product that we've been commercializing for a while. You can buy it in a web shop, but before you buy it, see how it works. So this is what I plan to show you here now. I'm not sure if you would be listening to a small tune. So the music is not that important. So if you really check, these little dots are actually the plastic version of the silicon substrate that I showed earlier that we use to trap these bubbles. Again, the music is not the best. So here you see an actual real-time movie, and then we zoom in and look at the high-speed recording. And all these bubbles are chemically active. And well, just earlier this year, we published one more study, because we have been doing more research on this new type of reactor to improve the advanced oxidation combining with some catalyst. And we have also used it for emulsification. So we improve the desired factor, so the diameter of the particles. We are still not performing that good in the energy efficiency, but obviously that can be worked out. And just a small side line, which came as a collaboration with this water utility company I mentioned earlier. We have also developed methods to demonstrate how our, let's say, bubble bag works better, or in this case, replacing a traditional line with a reverse osmosis plant. And well, I will leave this here. I think there's not much time to talk more into this, but they will be in the slides, and I'm open to explain how we are using a very simple method to demonstrate how better a new technology is compared to existing ones. And since Ono also mentioned something about education, I want to drop here another small advertisement. We have recently written 2 big articles on process intensification and the challenges in educating the engineers of the future. And I think it might be relevant for the audience. I reached my 10 minutes. I would like to thank you all for listening. And if you have any questions, so I'm more than happy to answer them.
Thank you, David. I was already familiar with the famous bubble bags, but it's always impressive to see the ultra high-speed videos. And I'll be interested to read the review in chemical engineering education. Do you have any follow-ups from the audience? I can ask many questions because it's very close to my area of research, but I don't want to monopolize the conversation. Okay, then I'll just do it to warm up the
floor.
Yeah. So, I mean, it's a bit silly question, but do you scale it up with many bags or with bigger bags?
Both should work. It all depends on how you design the acoustic field in the ultrasonic bath. So there are a few approaches. You could directly glue piezo's in the proximity of where you have these sort of modified walls of your reactor. But you could also think of a bigger ultrasonic bath where you know you have nodes and anti-node planes, and then you strategically put these pits where you know that you will have the maximum production of bubbles, and the rest typically is dead already. So you could make the bubbles bigger, but not necessarily make them more effective. So you could think of actually numbering up. So you could have a medium size of these bags connected in a series or parallel, even So there are different avenues.
And okay, and if you pack the system with lots of bubble bags, do you have problems with attenuation then, because of all the bubble clouds that intervene layer after layer?
Yeah, so far the system we have explored typically has the piezo source on the bottom, and the back walls are perpendicular. So there's very limited, that's why we also try to make it in a triangular shape, so that the next line of bubbles is at a different plane.
Yeah. And you touched upon this topic, but I probably missed the point. Is it not very energy intensive?
Well, it depends. If you use ultrasonic horns, indeed, the tip of the horn puts a lot of energy. But typically, the ultrasonic bath is the opposite. So you actually stick some piezos, and a lot of energy is diffused and lost into heating of the liquid by mechanical vibrations of the whole system. So you lose a lot of energy there. So we haven't really looked into, or we haven't got money to design novel type of reactors that we could combine the design of the piezo, let's say the sound source, and these sort of mechanical modifications to promote bubble nucleation.
Okay, well, I can keep asking questions, but I wonder if anyone else wants to chat with David. And if not today, then you can have his contact information and you can follow up with him later. Okay, so we will start wrapping up today's webinar. Thank you again, David, for a nice presentation.
Thanks for the opportunity.
I would like to thank again our keynote speaker and all our panelists for a very, very engaging discussion. And I would like to thank our audience for being so engaged as well in the discussion, and for always contributing the extra opinions on the propositions that are missing from our polls. Next week, we have the last webinar on process technology for food and pharma. We hope to see many of you next week, and we hope that you will advertise the event with your colleagues that are interested in food and pharma. Thank you very much, everyone. And virtual round of applause to the speaker and the panelists and all the contributors. Thank you very much.